All right, today we're going to build a fortress, not with stones and mortar, no, but with code and strategy. We're going to put together a modern defense for the invisible plumbing that powers our entire digital world, APIs. So the very first thing we have to accept, the first rule of this new world, is that the old way of thinking about security, it's just obsolete. The idea of a single strong wall protecting a trusted inside from a dangerous outside, it just doesn't work anymore. With cloud services, remote work, and all our apps talking to each other 24/7, that perimeter has completely dissolved.
And this slide, it just captures that shift perfectly. The old castle and moat model basically assumed that anyone who got past the front gate was safe. The new reality, it demands what we call zero trust and defense in depth. And the core idea is simple but powerful. Trust no one. Verify everything, always. And you build multiple overlapping layers of security, so if one layer fails, another one is right there to catch the threat. Honestly, this isn't just a good idea anymore. It's absolutely non-negotiable.
So here's our blueprint for the fortress. We're going to cover 5 key areas. First, we'll talk about why we have to move beyond the castle wall. Then we'll get into the real nuts and bolts: authentication and authorization, managing API requests, stopping common attacks, and finally, the watchtower, logging and monitoring. Okay, let's kick things off with our first section, beyond the castle wall. Like we said, our data and our apps are just everywhere now. They're scattered across different clouds, on our phones, you name it. A single perimeter defense is kind of like trying to guard an entire ocean with a single fence. It's just not practical. So this brings us to our first real layer of defense: authentication and authorization. This is the bedrock of API security. Before your API does a single thing, it has to get solid answers to 2 fundamental questions. Who is making this request? That's authentication. And then, are they even allowed to do what they're asking for? And that's authorization.
So authentication is all about proving you are who you say you are. And the good news is we don't have to reinvent the wheel here. We rely on these really robust industry-standard protocols. For apps that people use, that's often OAuth 2.0 and OpenID Connect. For secure server-to-server communication, you might use simple API keys, or for an even higher level of trust, Mutual TLS, which is where both the client and the server have to show their credentials to prove who they are.
Okay, so the server has verified the user, and it hands them a digital key, usually a JWT, a JSON Web Token. But now, the application on the user's end has a brand new problem. Where do you safely stash this key so you can use it for the next request? And this question, well, it opens up a really critical security debate.
Now, what's really interesting here is the trade-off it reveals. You've basically got a few options. Storing the token in local or session storage is super easy, but it leaves you wide open to cross-site scripting or XSS. If an attacker can sneak a malicious script onto your page, they can just read the token and walk away with it. On the other hand, you could use HTTP-only cookies. JavaScript can't touch these, which is awesome protection against XSS, but they can be vulnerable to a whole different attack called Cross-Site Request Forgery, or CSRF, unless you're really careful about configuring the same site attribute. The most secure option is storing it in memory, but the token just vanishes on a page refresh, which isn't a great user experience. So the key takeaway here is there's no single perfect answer, just a series of trade-offs you have to understand and manage. Okay, our gate is secure. We know who's coming in. Now it's time for our next section, managing API requests. This is our crowd control layer. We've got to manage the volume and frequency of requests to stop our fortress from getting totally overwhelmed, whether it's by accident or a full-on attack. And the tool for this job is called rate limiting. It's absolutely essential for protecting against things like denial of service attacks, where a hacker just floods your API with requests until it crashes. It also ensures fair usage, right? So one buggy script or a single power user can't hog all the resources and ruin the experience for everybody else.
One really popular way to do this is with the token bucket algorithm. Just imagine a bucket that gets, say, 10 new tokens dropped into it every second. Every API request that comes in has to take 1 token out. If the bucket's empty, sorry, the request gets rejected. This is a great model because it allows for short bursts of traffic. If a user needs to make 5 requests all at once and there are 5 tokens, no problem. But it still enforces a steady average rate over time.
Now, the other classic approach is the leaky bucket algorithm. For this one, think of incoming requests as water pouring into a bucket that has a tiny hole in the bottom. Your API processes requests at the constant steady rate of that leak. If requests pour in faster than the leak, they just queue up in the bucket. And if the bucket overflows, new requests get dropped.
The key here is that the output rate is always constant and totally predictable.
So, which one do you choose? Well, it really just depends on what you need. Token Bucket is super flexible and it's great for services where traffic naturally comes in bursts. Leaky Bucket, on the other hand, is simpler and gives you a very predictable, steady flow, which is fantastic for protecting your backend systems from any sudden, massive spikes.
All right, let's move on to our third layer, preventing attacks. So we've authenticated our users, we're controlling their traffic flow, now we need to inspect the contents of their requests to defend against some of the most common and devastating attacks out there.
So check this out. This slide shows a classic stored cross-site scripting, or XSS, attack. An attacker, just pretending to be a normal user, posts a comment on a product. But hidden inside that seemingly innocent comment is a malicious script. The web shop, not knowing any better, just saves that comment to its database, script and all.
Let's break down exactly how this heist works. Step 1, the attacker injects the script. Step 2, the server innocently stores it. Step 3, some poor innocent victim, let's call him Bob, comes along to read the product reviews. When his browser loads that malicious comment, boom, it executes the script. And step 4, well, now that script can do anything Bob can do. It can steal his session cookie, make purchases in his name, you name it, all because the application trusted the data it was sent.
The fundamental rule here is brutally simple. Never, ever, ever trust user input. The #1 defense against XSS is to sanitize and escape all data before you ever display it. What that means is you treat it as plain text, not as code that's meant to be executed.
Okay, now here's a related attack, Cross-Site Request Forgery, or CSRF. This is where an attacker tricks a logged-in user into, say, visiting a malicious website. That page then secretly sends a forged request to the web shop, maybe to post spam comments. The user's browser helpfully includes their session cookie, so the web shop thinks the request is legit. But as you can see in this diagram, we can stop this cold by using a secret, unique CSRF token. The malicious site has no way of knowing or guessing this token, so the forged request just gets rejected. Simple as that.
And, of course, we can't forget the granddaddy of them all, SQL injection. This happens when a hacker enters database commands right into an input field, like a search box. If the application isn't careful, it might just run those commands, potentially deleting your entire database. The defense for this is simple, and it is absolutely non-negotiable. Always use parameterized queries. They guarantee that user input is always treated as data, never as a command to be executed.
Okay. We've built our walls, we've checked IDs, we're managing the crowds, and we're inspecting all the packages coming in. It's time for our final active layer, the watchtower. This is the system of logging and monitoring that lets us see what's happening across our fortress and spawn an attack as it's unfolding.
Good security hygiene here is just critical. First off, never send detailed error messages back to the user. An error like database connection failed for user admin is an absolute goldmine for an attacker. Instead, just send something generic like an internal error occurred. But on the server side, you log everything in painful detail. This lets your team debug problems while keeping your system's secrets safe. Then, you use all that rich log data to monitor for unusual patterns in real time.
And there you have it. That's our fortress. The principles are really clear. We enforce strong identity checks, we control traffic with rate limiting, we validate every single piece of input, we monitor all activity continuously, and we do all of this with that zero-trust mindset, always assuming an attacker might already be inside the walls. So the final question I want to leave you with is this. Take a hard look at your own applications and APIs. Is your digital fortress a modern, multi-layered defense that's actually built to handle today's threats? Or is it still relying on a castle and a moat from a completely bygone era?